CBT Nugget's Network Plus series, LAN Technologies. Well, as we get deeper and deeper into this Network Plus series, obviously we're going to start to look at some concepts we've already covered or we've already kind of introduced previously. And of course, this is one of those nuggets as we look at local area networking, and we've already talked about several aspects of local area networking, but we're going to get specific now as we look at some things, some technologies and topologies and terminology that relate specifically to LANs and Ethernet. This nugget's going to be partitioned into three different areas. First of all, we'll talk about the various LAN standards. I'll define really once and for all what Ethernet is, and then we'll look at some of the 10 base, 100 base, 1000 base, and 10 gigabit base technologies. We'll also look at some of the LAN properties. We'll define terminology like carrier sense multiple access collision detection. Talk about broadcasts and collisions, good stuff like that. And then we're going to look at LAN topology, specifically four topics that are part of section 2.7 of the CompTIA Network Plus objectives. And that's logical network topologies like peer-to-peer, client-server, VPN, virtual private networking, and VLANs. Sound good? Okay, let's take a look. A local area network is a grouping or a network of computers and other components that have relatively close geographic proximity to one another. So a local area network is localized to a limited area. Now, LANs can vary widely in size. It can be basically a few systems that are connected to a hub or a switch, or it could be an extended local area network where the switch is going to connect to a router which itself may be connected to other switches, and of course those switches have ports that connect to end user systems, laptops, workstations, printers, plotters, things like that. So a local area network can be a handful of computers, a half dozen computers, up to hundreds of computers. Some local area networks can be above 1,000 computers. For practicality, most Ethernet local area networks are going to top out at about 2,000 nodes. Now, as I mentioned, the components of a local area network are typically going to be end-user devices like PCs and departmental servers and laptops, the switches, which uplink to a router, and of course all of these devices are going to have network interfaces or network interface cards in them. So the workstations and the servers may have network interface cards in them. They can either be modular devices that can be placed into the chassis, or they can be built into the system board or the motherboard. The network interfaces on a switch or a router, those will be integrated most likely into the device itself, but those devices can also be modular, and you can add additional what we call port density by adding additional ports. And we're going to talk more about these devices in greater detail, these switches and these routers, and we'll go and take a look at some of the ones in my rack in an upcoming nugget. Now, what do local area networks do for us? Well, they provide users with communication and interoperability and productivity applications. They provide resource sharing among human beings and systems. We've got data, we've got applications, we've got physical resources, which can be all different types of input devices. For example, right now I'm using a Wacom tablet, and a pen is my input device to allow me to write on this screen. They can be cameras. They can be output devices like printers and plotters. And of course, the local area network is also going to be made up of other communication paths to other local area networks through a router or a multi-layer switch. LANs can be all different types of sizes. They can be small office home offices like the one I have here. They can be what are called remote offices, branch offices, robos, or they can be what we call enterprise, where you've got thousands or tens of thousands of hosts. Now, let's talk about Ethernet, because we're going to be looking at Ethernet standards throughout this. This is the ubiquitous LAN standard out there in the world. Ethernet was originally developed in the 1970s by DEC or DEC, Digital Equipment Corporation, along with Intel and Xerox. This was called the DIX Ethernet. Later it became thick Ethernet because of the thickness of the cable. We talked about coaxial cable earlier in this series. The early thick Ethernet used that thick coaxial cable, and it transmitted data at 10 megabits per second. In the 1980s, the Ethernet standard was updated to give it more capability, and this was called Ethernet version 2. I'll just put ETH2. Now, the IEEE is a professional organization that comes up with networking standards. And the IEEE standards are the predominant LAN standards throughout the world today. In the mid-1980s, a EEE work group defined new standards for Ethernet networks. And these set of standards was called Ethernet, originally 802.3. Now, here's where the 802 came from. It was February of 1980. So 82 is where 802 came from. And this 802.3 standard was based on a process called carrier sense multiple access with collision detection. Now, we're going to talk about that a little bit later on, okay? I'm going to break that down. But today we talk about these standards simply as Ethernet. And by the way, after the 802.3, there's a wide number of letters and other symbols, letters of the alphabet, that can be here for different aspects of the Ethernet standard. And all of these standards operate at OSI layers 1 and 2, the physical layer and the data link layer. So Ethernet operates at the physical layer, and then it operates at the data link layer. We talked about the OSI model earlier, and there are basically two sublayers to the data link layer. You have the LLC sublayer and the MAC sublayer. The MAC sublayer is where we get that MAC address from, okay, the MAC addressing. So the MAC sublayer is an expert at dealing with the lower physical layer, and the LLC sublayer has expertise with dealing with, well, you guessed it, the layer above that, layer 3, or the network layer. It's the logical link control. That's where we get our logical IP addressing, so our logical IP address mapping to our MAC address. There is a interface, logical link control, between that. Just like there's an interface between the MAC address and the physical mechanisms that convert our ones and zeros and ones to binary to be sent across whatever media we're using. So we've defined Ethernet, and we'll further define CSMACD a little bit later on. Let's go take a look at our Ethernet standards here, and the first guideline we're going to look at is what's called 10-base-T. Now let's break this down. 10, this refers to the speed that's supported. In this case, 10 megabit per second. Base means it's baseband transmission or baseband Ethernet. In other words, there's just a single channel that data is being sent over, as opposed to, let's say, broadband, which has, data and video and audio like your cable that you get in your home. That's a broadband technology. Multiple channels, different types of traffic. This is baseband. So it's 10 megabit per second baseband Ethernet. The T means twisted pair, and you're familiar with that from earlier nuggets. So this is twisted pair, which we're looking at category 5 or above. And we know that category 5 is on the way out, so really category 5E or 6 or beyond. Now with 10-base-T, we've also got a segment length as well. It can only have a maximum of 100 meters. And that was an issue early on. That's why we used things like hubs and repeaters to kind of extend the physical geography of our local area network. And so because of those cable length requirements, we had to use some creative ways to extend the geography of our local area network. Now what we have here is 100 base TX and 100 base FX. 100 means obviously 100 megabits per second, and it is baseband, and TX means it's Ethernet over twisted pair. TX has a segment length of 100 meters. FX, however, is using fiber optic cable, not twisted pair cable, but fiber optics. And with fiber optics, 100 base FX, we can have now a cable segment length of 400 meters. 100 base T, this is 1000 base T, is what we call gigabit Ethernet. It's 1000 megabits per second, or 1 gigabit per second. It's baseband. And 1000 base T means it's going to operate over twisted pair cable. We're going to use all those wires, by the way, in the twisted pair. We've got 100 meters there. X, 1000 base X, means we're using fiber optic cable. And we can have beyond 100 meters, actually beyond a couple of hundred meters, depending upon the type of fiber cable we're using. Next we have 10G base, followed by several other abbreviations. 10G is 10 gigabit Ethernet. This is also known as 10GBE. It's also baseband. This is a standard first published in 2002. It's the fastest of the Ethernet standards available right now. It's 10 times as fast as gigabit Ethernet. 10G base SR is short range. This delivers data over multi-mode fiber, like we looked at earlier in this Nugget series. Over multi-mode fiber cabling, it has a range of about 26 meters or 85 feet. And depending upon the cable type, it can go up to 82 meters or 270 feet. Actually, with new types of cabling, it's actually gone way beyond that. Now, 10G base LR, this is long range. This uses single mode fiber, and this can go up to from 10 kilometers or about 6 miles all the way up to 25 kilometers, 25K, or 16 miles with no data loss. 10G base ER is extended range. This uses single mode fiber, or SMF, with a reach of up to 40 kilometers or 25 miles. These are the main ones you should know for your exam. There is also, I'm not going to go into all the details because you're not going to have to memorize all these specifications, but I want you to memorize these for your exam. There's also 10G base SW, LW, EW, and T. And you can see over here, for example, you can see an LW fiber port in this Nortel switch. 10 gigabit Ethernet, the fastest standard available. Now, carrier sense multiple access with collision detection is basically the way that Ethernet local area networks control the signals on their network. It's a very important aspect of Ethernet. Now, the carrier sense part of this means that all of the stations on the Ethernet are listening to the network media. Multiple access means that more than one node are accessing the media at a time. Now, as we know from earlier, this could be a bus topology where these are all tapped into a cable that's terminated on both ends, or this could be a hub, and this bus is actually inside of that physical hub device. Now what happens is, before transmitting, the computer listens to the network media. If the media or the hub is idle, then the computer will send its data. Actually, what it does is this. It says, do I have data to send? Okay? If it does, it will assemble a frame. Now, a frame is what we use with Ethernet. And remember, we have data using the OSI model, we have data that comes down, and it's going to use, let's say, either TCP or UDP at transport layer 4. So it'll place either a TCP or a UDP header on that data. That gets passed down to the network layer, where the IP header is appended to the data. Ultimately, this gets passed down, and this all becomes data, and it gets passed down to the Ethernet, and it frames it. It puts a header and a trailer on here. So this will eventually become what's called an Ethernet frame. So this station, if it has a frame, it will assemble the frame, and then it will basically listen to the media, and it'll ask itself, is some other station transmitting? If the answer is yes, it goes through a process called collision recovery. It's an algorithm. It's kind of a randomization process, and this is the collision detection process here. It'll keep listening to see if some other station is transmitting, and it'll listen back again on a random period of time. If nobody else is transmitting, it will transmit the first bit of the frame. If it detects a collision, which means another station is also simultaneously transmitting, it will go back and do that collision recovery process with the randomization algorithm. If it doesn't detect a frame, then it will keep transmitting the next bit until the transmission's finished. So basically, collision detection is a process that's used to improve the CSMA process by doing this collision detection process and terminating the transmission and going back to this recovery algorithm to reduce the probability of a second collision the next time it retries the process. Now, the extent of this network segment over which our collisions occur, this is referred to as a collision domain. So all of these nodes on this shared Ethernet represent what's called a collision domain. The size of your collision domain is going to have an impact on efficiency and data throughput. In other words, the more devices you have that are sharing this hub or this bus, the more the likelihood of collisions, which by the way are resolved in microseconds, but still it can have an effect on the network when you have dozens or hundreds of stations out there. Now, there are three major types of network communications, and we want to talk about broadcast, but we're going to talk about all of them, okay? First of all, we have what's called a unicast. And unicast is communication in which a frame is sent from one host and addressed to a specific destination. In a unicast transmission, there's one sender and there's one receiver. And the unicast transmission is the predominant form of transmission on local area networks and on the internet. One of the reasons why it's the most commonly used method is because instead of hubs now, we use switches. And these nodes connect into switch ports on the switch. And the switch itself, the intelligence of the switch, will be called the backplane. This is basically going to handle all of our traffic and basically creating bridges, independent bridges, transparently between all of these different nodes. So a layer 2 switch, as we'll talk about later, can actually remove this collision problem. Now, broadcast communication is where a frame is sent from one address, this node, to all of the other addresses. So you've got one sender, but all connected receivers are going to hear that. And broadcast traffic can also cause an overload on this Ethernet segment as well. The third type is multicast traffic. And this is where you have communication one not to all, but one to many, a specific subgroup of devices or clients. Unlike broadcast transmission, multicast transmission clients have to be members of the multicast group to receive that information. Now, we've talked about the other properties of speed. We know that we've got 10 base, 100 base, 1000 base. We know we've got 10 gigabit Ethernet. So we know our speeds, and we know that these different specifications of the 802.3 standard of the IEEE all have their distances. We know that single mode fiber offers us the longest distance, longer than multi-mode fiber, and longer than copper wire Ethernet or category 5 or 6 cable. Now, there's another term right here that I jotted down because this is one of the objectives for this particular section on the Network Plus exam. It's a term called bonding. And basically what bonding is, it's the ability to put, for example, in this switch or on a server, let's say this is a server connecting to this switch, we can have multiple network interface cards that are bonded together. This is also known as link aggregation. So bonding or link aggregation basically says this: we can combine two network interfaces and we can bond them together, and basically we can either increase the redundancy, so if one of these goes down, the other one's available, but we can also bond them together and get twice the actual bandwidth that we would normally get if we were just using a single cable or a single wire. So bonding or link aggregation is commonly used between servers and network devices to increase the capability, to increase the ultimate bandwidth of the communication between that node and the other nodes on that collision domain. Now, the Network Plus exam wants you to kind of understand 4 different types of kind of LAN technologies. And these are logical topologies that relate to local area networking. Early on, in the early days of networking, most networks were peer-to-peer networks, like the one we saw earlier with all of the different hosts that were connected to the logical bus or the hub. In other words, these devices had connectivity between the participants, and they communicated to each other using really their own network management. Let me bring up a diagram here real quick. These devices would connect to each other and have a communication channel with one another. Now, they could use a logical bus or a physical bus or a hub, but the bottom line is, if they shared files with each other, the files were stored locally on the host system. If a user logged on to a particular host, those user credentials, the username and the password was stored on a local database. So each system had its own local database for security management, its own network management, its own file management, its own files, and information and data were sent in a peer-to-peer network, one peer to the other peer. Files were shared in a peer-to-peer fashion, and protocols and services were handled in a peer-to-peer fashion. In other words, there was no centralized network operating system like a Novell or Unix or Windows system to manage these peers. And we see this same type of peer-to-peer technology emerging again today. We've got peer-to-peer file sharing that's used over the internet, and basically you've just got millions of these nodes or hosts using peer-to-peer networking over the global internet. You also see peer-to-peer networking, for example, with laptops. You may have a couple of laptops that are in a coffee shop or an airport, and these two devices can have a peer-to-peer or ad hoc network between them, and they can use infrared or they can use wireless technology and talk to one another. Handheld devices can create what are called personal area networks that are kind of peer-to-peer networks between handheld devices. So peer-to-peer networking is also kind of a logical LAN topology. Now, in the peer-to-peer network, all of the nodes or the hosts basically simultaneously perform as both the client and the server, serving up the data or the service. But in a client-server environment, you can have a server or a network operating system as the central point between these different nodes or these hosts. And the network operating system or the server can provide all of the data services, the network services, the messaging services, file transfer services, web services, email services, for example, the file and print services, all of these things on servers. And there's a client-server relationship where the client initiates a request to the particular network operating system server for that particular service or data or application that it needs, and of course the server responds to the client. Many times these devices, as they talk to one another and maybe authenticate to one another, are going to go through the security subsystem of the server or the network operating system. So a user may log on to a particular workstation, and they're actually logging on to a centralized database or a DS, a directory service, on this network operating system server. And typically you've got multiple servers that are located throughout the local area network and local area networks that are servicing these clients. So a client server architecture is a very popular architecture that's been used for a couple of decades in networking. And you use this client-server mechanism all the time, for example, on the internet, when you go up to websites and you have web pages delivered to your browser. That's a client-server relationship. Or you go up and you download a file through FTP, for example. Or maybe you go up and do online banking. You're leveraging web servers and database servers to do your transactions. Email servers are very popular servers. You've got emails stored up on a server, and you use some client like maybe POP3 to download your email messages to your workstation. So peer-to-peer and client-server are extremely popular LAN topology types. These are really more architectures, LAN architectures, than they are really topologies. Another LAN architecture or topology is what we call a virtual private network. What a virtual private network does is it takes our local area network or our corporate network here that is behind a router and a group of switches, for example, and we extend this private network, or we virtualize it over some untrusted network like the internet, or a telecommunications company's network, or a service provider's network. We extend our corporate local area network, corporate LAN, and all of its services and resources, its client-server architecture, all of its data and web services and email and chat and FTP and application services and mails services and database services and file and print services, terminal services. All these things get extended and virtualized over an untrusted network to some other remote site or a remote user. Okay, so it could be a remote user in a hotel or a kiosk or a coffee shop or a conference room or a conference center somewhere. Maybe they're using a laptop with some VPN client software on it, and we're extending the corporate LAN either in its entirety or a subset of our local area network or corporate network to that particular laptop. Same thing over here with the small office, home office, or remote office, branch office. We're virtualizing our private network over the untrusted network to a remote site. So we can have a site-to-site VPN or a remote access VPN. So a virtual private network is a way of virtualizing our local area network. We'll talk more about that later on when we look at security. Finally, we have a special kind of network called a VLAN, or a virtual local area network. We'll talk more about this later on when we deal with switches, but this is the classic Cisco diagram where we have a distribution layer switch, and these distribution layer switches, there's an uplink of several switches to this distribution layer switch. So if we look at our previous nuggets, this switch could be located in a server room or a data center or a wiring closet on the first floor. And then another area of the first floor and the second floor and the third floor, you've got a switch on each one of these floors. What we do with the virtual LAN is, instead of having one giant local area network here, we can say, regardless of where you're located, we can put you in the same local area network, or what we call a broadcast domain. Routers with their interfaces create broadcast domains. So for example, if we take this host on the third floor and this host on the second floor and this host on the first floor, and we put them in their own virtual local area network called sales, if one of these hosts sends out a broadcast packet, only these hosts in that broadcast domain or that virtual LAN will get that broadcast packet. That's why it's called a broadcast domain. It's partitioned off from the HR group or the engineering group, the VLAN. And this VLAN capability is all done with software on these switches, these layer 2 or layer 3 switches. So a virtual LAN is really a software feature that you implement on a particular switch. For example, I can take a switch with its port density. Let's say I've got 24 ports here, and I can logically on the inside of the switch say I'm going to take these 6 ports and put them on VLAN sales. I'm going to take these ports and put them on VLAN HR. I'm going to put these ports on VLAN engineering. And as the end hosts plug into those ports, they're on their own broadcast domain, their own virtual LAN. And by default, these devices are all segmented from one another. They're all in their own broadcast domain. So a broadcast domain in a VLAN is all pretty much synonymous with a subnet or a subnetwork. So they would all have their own IP subnet. So for example, from earlier, this could be network 10.10.1.0. This could be network 10.10.2.0. This could be subnetwork 10.10.3.0. So it also applies to our IP addressing as well. And by the way, at this point, all of these devices are in their own VLAN. They cannot talk to one another. They cannot send traffic from one VLAN to the other. In order to do that, we need a router. So we could either add a router down here to this topology, or as we'll talk about later, we can have a special switch, like this could be a layer 3 switch, L3, and this layer 3 switch could have a route processor on it, either a modular route processor that slides into the device, into the chassis itself, or the route processor can be built into the hardware of the layer 3 switch, and that can do the routing for us, routing packets from the sales VLAN to the engineering VLAN, and from the HR VLAN to the sales VLAN. So virtual LANs are another kind of architecture that we use for local area networking. Just like we virtualize our private network here over a wide area network, VLANs basically virtualize this over our local area networks, and it's another architecture, and we get this from using special software on layer 2 and layer 3 switches. Well, don't worry, we're going to revisit a lot of these concepts again over and over and over throughout the remaining, 15 more nuggets that we have in this Network Plus series. So don't worry, we're going to reinforce and reiterate a lot of these concepts. And you'll see this a lot throughout this nugget series. That's why it's so important for you to go through this Network Plus series twice if you can. Now again, in this LAN Technologies nugget, we looked at 3 main areas. Looked at LAN standards, LAN properties, and local area network topologies, or you can also refer to those as architectures. Okay? I hope this CBT Nugget has been informative for you. I want to thank you for viewing. See you next time.